Hi, Professor. Can I ask a question before we start?
Yes.
So I just want to ask about the homework problem 2. So I don't know how to prove the Newton is converged in linear rate.
Can you ask your question a little bit louder? I couldn't hear you. Hold on. Maybe I need to increase my volume here. Yeah, go ahead. Ask again. What's the question?
Yes, I want to ask about the question number 2 of the homework. It asks about proving the conversions rate of the Newton method is linear. But I don't know how to start with that.
Okay, so that for that particular example, the convergence of the Newton's method is linear. So all you have to use a recursion for the update for the gradient Newton method xk plus 1 in terms of xk, and then show that xk minus x, relate xk plus 1 minus x star to xk minus x star, and show that the factor that's sitting in front of it is something that's less than 1. Right.
Oh,
that's all.
I see. Yeah. So for the reason that is not super linear converge, do I need to prove anything specifically?
You need to figure out why. Yes, that's all. You just give a reason why. Yeah. I'm not going to tell you the reason why, because that's part of the question.
I see. Yeah.
All right.
Yeah.
Okay, so actually, yeah. Before we start, do you have any questions about the last lecture? We'll go over it briefly, just a review, because we're going to build on what we talked about last time anyway. So we're talking about optimization with equality constraints, and this, in some sense, is more general than the material we covered before, where we talked about in lecture 10, we talked about minimization over a closed convex set, right, with a non-empty interior, so if with these equality constraints, okay, you may not have a constraint set that's convex. It's going to be closed, but not necessarily convex. Okay, but on the other hand, it is specific to a constraint set that's constructed using equality constraints. So it's less general in that sense than a general set that might be convex and closed. So, and we saw, and the key result that we established last time was that under some conditions on the F's and the HI's, okay, and it turns out that should be a regular condition, then we showed that if X star is a local minimum of the function, then it must satisfy this condition. In addition to satisfying the condition that H of X star is 0, which is the constraint, it also needs to satisfy a condition on the gradient, which is given by this expression. Okay. And we define those two sets: the span of the gradients, and the space that's orthogonal to the span, which is the set of all z's, such that the gradient, the dot product of the gradient of each of the hi's with z is equal to 0. And this was called the space of first order feasible variations, and we explain why. Well, actually, this will play a role in some of the discussion we'll have today, which is why I'm repeating that here. We saw examples where you may not have a Lagrange multiplier. We saw this example, and then we concluded that one reason why this might be happening is because these gradients are linearly dependent, which is why we impose the condition that the gradients be linearly independent, and we call such x's for which the gradient of the hi's at x, if we put them all together, basically they are linearly independent. So if you put them all together in a matrix, that matrix is going to have rank m. Okay, and of course m has to be less than n for them to be linearly independent. Okay, and then we talked about then formally stated the Lagrange multiplier theorem, saying that if x is regular, then then we have the condition that we talked about earlier, the gradient condition we talked about earlier. Okay, of course, this is only goes one way. You could have the existence of Lagrange multipliers. In other words, when we say existence of Lagrange multipliers, we mean that there exists lambda such that this condition holds. Now, you could have a situation where x star is not regular, okay, for which these guys are linearly dependent, but still you have a lambda that satisfies this equation. Okay, and so we'll actually talk about an example of that in the next lecture. So it doesn't go both ways. So you don't have to have x be regular for there to be, but if x is regular, then we can prove formally that there will be, or there will always be, a unique, actually, a Lagrange multiplier vector. Okay, and the key behind the proof was the construction of this sequence of unconstrained optimization problems that we then relate to the solution to the constrained optimization problem that we were interested in. And basically, in the penalty approach, you add some things to the function and look at this function sequence of functions gk, and we showed that gk is we actually went through two steps here. We actually first constrained the optimization problem over gk of gk by constraining to this set S, which is the ball around x star, right? This epsilon ball around x star. Okay, and then we establish that the solution to these problems, actually, of the xk's converge to x star, and so basically we showed that for large enough k, the optimum solution to this constrained optimization problem is in the interior. And since it's in the interior, then it's also the solution to the unconstrained optimization problem, which we know what the necessary conditions for that are from the previous, what we did from lecture 1 to lecture 9, I guess. So so that's exactly what we exploited. So we first established that the solution to this constrained optimization problem goes to x star as k goes to infinity, and then said, well, this x for large enough k, xk has to be an interior point of S because x star is an interior point of S. Okay, and that was the key idea. Okay, and then the rest of it was just somewhat, just mechanics to get the condition. So one other key idea that we exploited was the notion of a pseudo inverse. So the fact that if you have a n by n matrix that's full rank, that has rank m, n bigger than m, and then A transpose A is an m by n matrix, and it has a pseudo inverse, which or Moore-Penrose pseudo inverse, which is given by this matrix. Okay, which if you multiply the matrix A on the left by this matrix, you get the identity matrix. Okay, so for non-square matrices that are full rank, okay, so you have to define. You can define inverses for multiplying from the left and inverses multiplying from the right. So and of course the these pseudo inverses are give you solutions to this equation, and solutions to this linear system of equations is not necessarily going to be unique, right? So we know that you should know from your linear algebra class. But anyway, so we applied actually the Moore-Penrose pseudo inverse in establishing that the middle term essentially in this gradient equation converges to some number, and we call that number the Lagrange multiplier. And we showed that basically, if that's the case, then that lambda has to satisfy this equation. Okay, so that's how we concluded that we have a Lagrange multiplier in the case of in the case that X star is regular. So, any questions about this? Is that clear? So now we're going to develop on this result, and the first thing we're going to do is establish second order necessary conditions, and then talk about a second order sufficient condition. Okay. And now that we made this connection between this constraint optimization problem and a sequence of unconstrained optimization problems, we can really borrow tools that we already developed for unconstrained optimization almost directly. Okay, and that's how we'll establish second order and necessary and sufficient condition. Okay, so are we all ready to go to today's lecture? All right. All right, so here's actually just a recap of the first order necessary condition. If X star is a local minimum of the constraint optimization problem, okay, and if the gradients of the HIs are linearly independent, then there exists a unique lambda such that this condition holds, the Lagrange multiplier condition holds. Okay. Now, of course, this there are two equations that we can use, and when we talk about sufficient condition, we'll mention that again. But basically, there's two sets of equations one can use. So there's this equation that's in terms of the gradients, and of course, X star also has to satisfy the constraints equation, right? Okay, and how many equations are these in total? So the first set of equations, and for the gradient, how many equations are contained here? Yeah.
N.
So actually, the gradient is n-dimensional, right?
Yes, n equations.
N as in Nancy. So the first equation will give me n equations, and this h x star equal to 0, the m of those. So these are m plus n equations. Okay. So, or n plus m equations. And how many unknowns do we have if we want to solve these equations, for example? How many unknowns?
N plus m.
Also n plus m. Okay. So there is some hope that we can actually find the solution, and the solution in some cases will turn out to be unique. Okay. So, can anyone think of, and we'll actually do an example a little bit later, but can anyone think of a case where the solution to these equations will be unique? When might that happen? One example. Just based on what you know from your linear algebra class. Now this first equation is already linear in lambda. Okay, but what if the constraints are linear? So this will give me m linear equations involving x star, and then I'll have n equations involving lambda, which are linear in lambda. But suppose we also have that these are linear, the gradients are linear in x as well. The gradients of the HIs and gradients of f. Suppose they're also linear, right? Then you'll end up with n plus m linear equations and n plus m unknowns. And so you'll have a unique solution. Okay, and we'll actually, emphasize that over and over again as we go along and talk about Lagrange multipliers. So that's so there are simple examples, at least, for which you can actually explicitly solve for the Lagrange multipliers along with x star. And then there may be, if x star is unique, that's the only one you need to check to see if it's a minimum or not. Okay, but if x star is not unique, and that can happen if these equations are nonlinear, in that case you'll have to check each of those x stars with using a second order sufficient condition to see if it's a minimum or not. Okay, so that'll be the procedure that we get to later. But let's actually establish the second order necessary condition now. Okay, so that was just a preview of how you use the Lagrange multiplier theorem in examples. All right, so let's look at this unconstrained sequence of unconstrained optimization problems we had earlier. This is just a repeat of what we had from last class. And we know that if xk is the minimum of this constrained optimization problem, with S being the ball around x star, epsilon ball around x star, then we know that xk converges to x star. And xk is an interior point of S for sufficiently large k. We use that in establishing the first order necessary condition. But since xk is an interior point of S, we can also, we also conclude that we can apply the second order necessary condition for this unconstrained optimization of G. Wasn't there. So what's the second order necessary condition then for minimization of GK? Someone?
Professor, can you repeat what you just said? Because I think you froze for.
I did?
I couldn't hear you for like 1 or 2 minutes.
1 or 2 minutes? Wow. Okay. All right. Let's start over. Yeah. I don't know what happened there. Okay. So the question is can you guys? I'm going to send a chat message.
You're back now.
Oh, okay. So now I don't show any issues on my end. So can you guys hear me still?
I can hear.
Okay. All right. So send me a chat message if you can't hear me, because I can't really tell in my. For large K, right, for sufficiently large k, the minimization of gk over the constraint set S is the same as unconstrained minimization, because we know that xk becomes an interior point of S for large k, because xk is converging to x star. So what's the second order necessary condition for unconstrained minimization of gk? Okay. Okay, so I
It's back now. It froze about 2 minutes ago.
should I restart? Maybe that would be the safest thing. I'm not sure what's going on. Okay, did you guys hear my question?
Yeah, so it just needs to be greater than 0.
What needs to be greater than 0?
The Hessian.
The Hessian, okay. So Hessian at xk needs to be positive semi-definite, right? That's the second order necessary condition for unconstrained minimization. So we know that will still hold for gk even with the constraint, because xk is an interior point. Can you guys still hear me?
Yes.
Yeah.
Yes.
Okay.
Yes.
All right. So now we need to compute the Hessian of gk. So we computed the gradient before from last class, right? So we just have to take another derivative essentially, right? So when we do that, we get from the gradient of f, we take that, the gradient of that, you get the Hessian of f. And then you have to worry about the middle term. The middle term will apply a chain rule essentially, or product rule, I guess. And the first thing we do is we can fix the gradient of hi here, and then take the derivative with respect to this. And again, verify this at home for yourself. Convince yourself by expanding things out and taking the derivative component by component. But basically, you end up with a matrix, and then that matrix, for when you fix the gradient and take the gradient with respect to LH, you end up with this matrix. Okay, the sum of these matrices. And then when you do it the other way, you get the Hessians of the HIs. And then finally, if you look at this guy, x, okay, x star is fixed. So you take the gradient with respect to x. This is linear function, so you just get the identity matrix. Okay, so that's the Hessian of gk. And the constraint is that Hessian has to be positive semi-definite for a large enough k. All right, I'm going to do another mic check. You guys still hear me?
Yes.
Yes.
Okay. All right. All right, so now let's apply that. This is just a repeat of that Hessian, right? I've just repeated that equation here. Now I'm going to exploit the fact that Hessian is positive semi-definite, which means that this right-hand side is positive semi-definite, okay? All right, now I'm going to use this to establish a second order sufficient condition, a necessary condition, okay, for F, for the optimization of F. Okay, to do that, I'm going to introduce I'm going to reintroduce this set V of X star. Remember, V of X star is a set of first order feasible variations, right? So if Z belongs to V of X star, that means that that Z is orthogonal to all the gradient HI terms. Right? So let's take a Z that belongs to V of X star. That means Z that satisfy those conditions. And I'll define a ZK as follows. So ZK is defined by taking Z and subtracting out this term here. So it looks like a strange term, but I constructed this in a specific way so that the gradient of, if I take the gradient of H at xk and take the dot product with zk, I'll get 0. So why is that? So anyone recognize this this matrix here? What is this matrix? Remember,
It's a pseudo inverse.
Yeah, it's a pseudo inverse of the gradient of the gradient matrix, right? Of H. So all the H functions, their gradients put together into a matrix. So that's the pseudo inverse of the Moore-Penrose pseudo inverse of the gradient of H at xk. Okay. Now, so why does it why is this inner product going to equal 0? So let's just multiply it out. So if I take the inner product of this with zk, I'll get the inner product of that with z. Minus, now when I plug in here, say gradient of H of xk transpose, then by this, so I get this matrix here times this matrix, which is its inverse. So that will give me the identity matrix, and I'll just be left with this term here, which is exactly what the first term was. So this is equal to 0. Okay, so now if I'm going to exploit this fact that this inner product is 0, right? So if I look at this, so if I take this matrix, gradient of H xk transpose, and pre-multiply it by this guy here, right? Sorry, I didn't mean to say that. If I take the zk vector here and zk transpose this matrix here, that'll give me 0. And post multiplying this by zk will give me 0 as well. So if I pre-multiply this matrix by zk transpose and post multiply it by zk, then this guy should disappear. And only this term, and this term will remain. Okay, so that's what I'm going to do. So if I did that, then that middle term, let me see if I can make it a little big so we can see both equations. So basically, when I pre-multiply by zk transpose and post-multiply by zk, and put everything in this equation in the middle there, this term can be ignored because that's going to go off and be zeroed out. So I'll be left with this term, and this term. And I know that that has to be positive because this matrix is positive semi-definite. Okay, all right. So, I keep saying positive. I mean non-negative because that is positive semi-definite. Okay. So if I put that there and then K, that's the third term in that left-hand side. Hessian plus alpha I. Okay, so now I'm going to let K go to infinity in this equation. Okay, if K goes to infinity, then what happens? So as K goes to infinity, of course, we know that xk goes to x star. That we already showed. Not x sub k, this should be superscript k. Goes to x star. Now, k times hi of xk, let's go back to lecture 11. K times h of xk we showed goes to the lambda vector. So if you look at the ith component, it goes to lambda I. So this goes to lambda I. Okay. What about zk? What does zk go to? So let's look at zk in the equation. Right? So what's happening with zk? Anyone want to guess what zk goes to? I'll just remove this here for now. So the equation for zk is more clear. So what does zk go to? Yeah, anyone?
0.
Not 0. What we know is that this xk is going to x star, and the gradient of hi at x star times z is equal to 0, right? So each of these guys, when I multiply by z, is going to go to 0. So this whole thing will go to 0. So that means this will go to 0. So zk goes to z. Right? Everyone see that?
Yep.
Okay. So zk goes to z. All right. Okay. So let's put it all back in that equation. But these take the limits in this equation essentially. So zk is going to z. This guy is going to the Hessian at x star. Of f at x star, I mean, plus k times hi of this k times the hi is going to lambda. Right? So I get lambda I there, and then I get the Hessian of hi at x star plus alpha times I. And this is for all z belonging to v of x star. This equation holds. Okay. So this is the second order necessary condition. But of course, alpha was under my control, right? I defined alpha. I defined this function g with the alpha in here. So I can make alpha as small as I want. Okay, this is something I just created, right? So that's what I'm going to do next. So this is what we just concluded, that z transpose times this matrix times z is positive. By the way, if this condition were to hold for all z, that means that the inner matrix would be positive semi-definite. I'm not saying that this inner matrix is positive semi-definite. All I'm saying is that this product is going to be positive for all z belonging to v of x star. Not all z belonging to Rn, but just for z's belonging to v of x star. Okay, so that's the second order necessary condition. Now I can make my alpha go to 0 and get rid of this. So then I'll have only the things that are in my original problem, which is the F's and the H's. So the F and the H's are the only thing that will appear now when I take alpha equals 0, and I get this equation as my second order necessary condition. Okay.
What's the meaning of the Vx star again?
So Vx star is basically all the z's. Z belonging to Vx star means that z is orthogonal to all the gradient of hi's. Or you can think of Vx star, as we said in the last class, as all the first order feasible directions that you can take from x star. Okay, so if you want to think about it geometrically that way, let's see where we define V of x star. Oh, no, yeah, it was here. Okay. So V of x star is defined as this set. Okay, and V of x star can have a much lower dimension than n. Okay, right? So it actually, what is the dimension? So suppose I have m orthogonal vectors that are these gradients, and I'm looking at all vectors that are orthogonal to this set of vectors. What's the dimension of that space going to be?
N minus m.
N minus m. That's right. So it's so in general, if m and n are close to each other, this is going to be a much lower dimensional space than the original n-dimensional space, right? And so meeting the second order sufficient condition, a necessary condition on that n minus m dimensional space is going to be much easier than meeting it on the original n-dimensional space. So it's quite likely that I'll be able to meet this condition for all this condition for z belonging to V of x star, but it doesn't hold for z outside of it. Okay, so that means that this may not be a positive semi-definite matrix, but still this condition could hold for only if we only restrict ourselves to z belonging to V of x star. Okay, so that's the second order necessary condition. That's how we bring the constraints in into second order necessary condition. Okay. And you can follow the same procedure. In fact, this is almost identical to now what we did with unconstrained optimization. And the steps are similar that I'm not going to go through it, but there's a short argument given in your textbook that you can look at, or you can try and derive it on your own. It's quite easy now that we got to this point. So you can actually show that there's a corresponding second order sufficient condition. And basically, just like with the second order sufficient condition for unconstrained optimization, we went from positive semi-definiteness to positive definiteness to conclude to get sufficiency. The same kind of thing happens even here. So basically, what we show is that if x star is regular, and of course x star is feasible. I should probably mention that as well. X star, that is, it's always, we only care about things that are feasible, for which h of x star is 0. Anyway. So suppose x star is feasible and regular, that is that this matrix has rank m. If there exists a lambda, so this is a sufficient condition, right? So if you can find a lambda such that this is equal to 0, and the second order condition now says that this product has to be strictly positive, not just greater than or equal to 0 for all z belonging to V of x star, then you can conclude that X star is a strict local, it's actually going to be a strict local minimum, just like we had with the necessary condition, a local minimum for this optimization problem. Okay, so that, you know, so when you're trying to find, you know, analytically find solutions to the constraint optimization problem, what you'll do is look at the equations that you would get. These so you would combine this equation, the gradient equation, with the hi of x star equal to 0, solve these m plus n equations for lambda and x star, and for each of those solutions, so for each, there may be multiple x stars, and for each of those x stars, there will be a corresponding lambda. So lambda is only unique for a given x star. Okay, so you solve those equations, get the lambdas in terms of the. Actually, I should maybe emphasize that point again here. So these equations can be nonlinear in x star, but they are linear in lambda. So once you find a solution for x star, the corresponding lambda will be unique, because this is a set of linear equations. Okay, so you can divide up the solutions that way. So you may have multiple solutions for x star, and for each of those x star, you will have corresponding lambda, a unique lambda. Okay, and then you check each of those x stars for the and the corresponding lambda for this condition. Okay, and if it holds, then you can conclude that it's a local minimum. Okay, so that's a procedure we're going to use when we solve, at least solve analytically, equality constraint optimization problems. Okay, right. Let's actually repeat that by defining what's called the Lagrangian function, and write everything in terms of this Lagrangian function. Okay. All right. So what is the Lagrangian function? And this will actually play a role again when we talk about something called duality. But let's define Lagrangian function first. So it's f plus the linear combination of the h's. So this is a function of both x and lambda. Okay. Notice that it's a linear function in lambda. Okay. And in general, it's going to be nonlinear in the x. All right. So if x, then let's write the necessary condition in terms of this L. So if x star is a local minimum and regular, then there exists a lambda such that the gradient of this, so since it's a function of two variables, let's look at the gradient with respect to x. So we'll put an x underneath here, just to say that we are doing the gradient of this L function with respect to x. And so we know from the first order necessary condition that the gradient of this function with respect to x, which will give me gradient here and gradient here, will be equal to 0. Okay, and you could also think of the constraint h of x star equal to 0 in terms of the gradient of L with respect to lambda, because if you take the gradient of L with respect to lambda, this goes away, and you basically say that each of the hi's should equal to 0, hi of x equal to 0. Okay, so that's another way to write it. Although you don't, I mean, that's just this will actually might become might be interesting when we talk about duality, but at this point, it is just a neat thing that you can write h of x star as the gradient of this L function with respect to lambda. Okay. Okay. So again, as I mentioned, this is m plus n equations and m plus n unknowns. Okay, and then the second order necessary condition is given here. And similarly, for the sufficient conditions, okay, if the second order sufficient condition, if x star that's feasible and regular, if there exists a lambda such that the gradient of L is 0 and this condition holds, that means this product is positive for all z not equal to, oh, did I mention z not equal to 0? Okay, it can't be positive and z is, oh yeah, that's right, for all z not equal to 0. This is same as what we had for a sufficient condition without constraints, right? We can only have positivity here if z is not equal to 0. And then z belonging to v of x star. Then x star is the local minimum for this optimization problem. Okay. So we can use these equations to solve some simple constrained optimization problems. Just like, you know, in your calculus class, you used the derivatives to solve, so to get solutions to some simple optimization problems, right? And again, unconstrained optimization problem, earlier in this class, we could just use our gradient and Hessian to solve some simple problems, typically quadratic type problems. You could solve explicitly using those conditions. Okay. So we can do the same thing with constraints now, using these results. Okay. And by the way, yeah, these constraint optimization problems, a lot of them do appear in applications, and you can solve them explicitly for certain applications. Of course, in general, of course, when these f's and hi's could be complicated nonlinear functions, you may not be able to solve explicitly, and then you would have to rely on numerical methods, gradient descent type methods. And we'll actually talk a little bit later, after your midterm, we'll talk about ways to compute computational methods for these kinds of optimization problems. But for now, let's stick with simpler problems for which we can give exact analytical solutions. Okay. All right. So, and you'll do a couple more of these in your homework that's due on Tuesday. Actually, yeah, we've been going for quite a while, right? So should we take a short break? Let's take a short break, and then we'll do the examples. Any questions? The results will become much clearer once you start, applying it to simple examples and solving them using those equations. Okay, I guarantee that. So let's take a couple minutes break and come back at 11:47. Okay. All right, any questions before we start the example? Okay, let's do the example. Someone say something so I know that I'm not frozen.
No
I can
question.
hear you.
Okay.
No question.
So let's look at this example. So this is my f of x, and this is my constraint h of x equals 0, right? Okay. So h of x is x1 plus x2. Come on, okay. Plus x3 minus 3 is equal to 0. And my Lagrangian function, which is the combination of f and the h. There's only one h function, one constraint function. Plus lambda times h function. Okay. So I need to compute the gradient of the Lagrangian function with respect to x. So the gradient of f is what? So if I look at the gradient of f, the gradient with respect to x1 will give me just x1, 2x1 divided by 2 is x1. Gradient with respect to derivative with respect to x2, sorry, it will give me x2, and then the third one will be x3. So the components of the gradient are just x1, x2, x3 in this case, which we can write this as the tuple, or equivalently, it's the column vector. Okay. And the gradient of h, it's linear, so
All ones.
all ones, very good. Right. Right. Well, what's the rank of this gradient of h then?
1.
It's just 1. And so rank is equal to m. M is equal to 1 in this case. So so this means, and this is not a function of x. So this means that every x is regular. Okay. So you could have a situation where you have only one constraint, and the gradient can be non-regular for some values of x. For example, if the gradient of h were x1, x2, x3, for example, then when the x vector is 0, I get the gradient being 0, and that's not a rank 1 vector, right? So that can happen, right? So it's not, but in many examples, all x that you can possibly consider or all x that satisfy the constraint are going to be regular. Okay, let's look at the first order necessary condition by setting the gradient of the Lagrangian to 0. So if you set the gradient of the Lagrangian 0, so I'm taking a linear combination of this guy and setting it equal to 0. There's only one lambda to consider. So the first component will tell me that x1 star plus lambda is 0. The second constraint will tell me that x2 star plus lambda is equal to 0. And the third one. Okay. So this means that the x's are all equal to each other. x1 star is equal to x2 star equal to x3 star. And they're all equal to minus lambda. Now, we still have a fourth equation that will allow us to solve this exactly. And the reason why we have a unique solution in this case is because the Lagrangian is linear in both x and lambda. The gradient of the Lagrangian is linear in both x and lambda. So you have a set of four linear equations in linear constraints. So you get a unique solution, right? So that the fourth equation tells us that h of x star is equal to 0, but that means that if you look at what h of x is, it's the sum of the x stars, and that's minus 3 lambda. So this means that minus 3 lambda minus 3 is equal to 0, which implies that lambda is equal to minus 1. And x star is equal to what?
1.
All ones, the all ones vector. Right? So x star is the unique candidate for a local min. Okay, it need not be a local min, right? It could be a local max actually, right? But x star is the local, so we can check to see if it's a local min or not. And to check if it's a local min or not, we can use the sufficiency condition. So the sufficiency condition for this, there's only one thing to check the sufficiency condition on. So let's look at the Hessian of the Lagrangian. The Hessian of Lagrangian is the Hessian of f plus lambda times the Hessian of h. There's no h. There's only one h. So there's no hi. It's just h. But if you look at the Hessian of f, the Hessian of f, you get the identity matrix, right? From here, identity matrix. And the Hessian of h, what is that? Since the gradient is constant, when you take the next derivative, you're going to get 0. So you get the identity matrix plus lambda times 0. So this is just the identity matrix, which is positive definite. So this means that x star is a strict local min for the optimization problem. Let's call that P1. Yeah, we call that P1 there. So the constraint optimization problem has the vector 1, 1, 1 as a strict local minimum. Okay, so now the question is this a global min as well? Okay, so how do we check to see if it's a global min or not? Okay, so one thing we can see is that we can try and apply something we know from lecture 10 on optimization over convex sets. So that's one approach. So this is a convex function, and this constraint, right? This constraint set. So all the x's that satisfy this constraint. That set h. So h is remember h is a constraint set. Is all the x's such that constraint satisfied. Now this constraint, in this particular case, we know it's closed, but we also know something else. This is a hyperplane, so it's also convex, right? It's clearly also convex. So we're minimizing a convex function on a closed and convex set. So what do we know about that? Those kinds of functions?
They achieve maximum.
Yeah, so it's a minimum first of all, the minimum exists, and if the gradient condition is met, then you get the global minimum, right? So any local minimum is also a global minimum for those kinds of functions so convex sets, convex functions on closed and convex sets. We know that every local minimum has to be a global minimum as well. And there's only one candidate for a local minimum, so it must be a global minimum. So that's one way to do it. Okay, so that's exactly what I say on the next page here. So F is convex, and this constraint set is convex and closed. Therefore, X star, which is a local minimum, has to be a global minimum as well. Okay, but there's another way to conclude this, and this might be this other alternative way might be useful in other problems where the constraint set may not be convex. As I said, that equality constraints always result in closed constraint sets, but they may not be convex. So you may apply something else to conclude that it's that you have a global minimum, right? If the function is convex. Okay, so this is a slight extension to Weierstrass's theorem, with the corollary to Weierstrass's theorem, which maybe I should have stated it this way when I first started, but I didn't want to complicate it too much. I guess that's why I didn't do it. Okay, so remember Weierstrass's theorem. It says that if f is a real valued continuous function on a compact set, then f achieves its minimum and maximum on S, right? But then I said that if f is real value continuous and coercive, then f achieves its minimum on Rn. So then we said that it achieves a minimum on Rn. Rn is not a compact set, so we had to separately prove it by actually constructing a compact set as part of the proof and using that, using Weierstrass's theorem to establish this result. Okay, but in this corollary, I needn't have just stated it for Rn here. Okay, so I could actually have in place of Rn any set S that's closed but not necessarily compact. Okay, if it's compact, you go back and you get it from Weierstrass's theorem. But if Rn is replaced by a closed set that's not compact, that means it's not bounded, then it still holds. So that's this, and that's the proof is essentially identical to this. So maybe you guys should try and show that on your own, but I give you the starting point of that proof, right? So the extension says that if f is a continuous function on a closed set that's not compact, and if f is coercive, then it achieves its minimum on S. Okay, so S is closed but not compact means that it's not bounded. So it's possible for x to go to infinity while x belongs to the set S because it's not bounded. So that if it was bounded, then it would be compact, then we needn't have gone through all of this. We just use Weierstrass's theorem directly. Okay, so for those x's that are going to infinity, we must have fx going to infinity by coercivity. That's a definition of coercivity. Then you apply the same steps as in the proof of the corollary. So you basically construct this, you construct another set, call it, and don't call it S, call it B or something like that. And these steps will still hold, except then you, instead of looking at the X star in S here, you'll have X star in S intersect B, where B will be defined like this. Okay, so but the steps are going to be identical otherwise, and you can conclude that there is an X star such that f of x star is less than f of x for all x and s. Okay, so if you want to see the steps of proof, you can also look at proposition 8.8 in the text, in the appendix. Okay, so we can apply this now. So we don't have to just use you don't have to, it doesn't have to be all of Rn, but it could be any non-compact subset of Rn that's closed. And as long as F is coercive on that, it'll achieve its minimum. And we can apply that result here to conclude also. If we didn't want to use the results from lecture 10, we could use this instead. So because basically this function is convex on the constraint set H, F achieves its, sorry, not convex, it's coercive. F is coercive. Why is it coercive, by the way?
It's quadratic in each term.
Yeah, so whenever the magnitude of x goes to infinity, and that can happen on this hyperplane, by the way. On this hyperplane, magnitude of x can go to infinity. It extends out to infinity in both directions, right? Or in three directions, I guess. And so you can conclude then that since this thing goes off to plus infinity whenever that magnitude of x goes to infinity, that it's coercive. So F achieves its global minimum when we say min without any qualification, it usually means global minimum. And since there's only one local minimum of F, then that local minimum must be the global minimum. So it actually didn't even exploit convexity here. So all you exploited is the fact that it's coercive on the constraint set, and the constraint set is closed. Okay. And of course, we also exploited the fact that there was only one local minimum. And so that means that has to be the global minimum. Okay, so you could use this approach, and you might find this more useful in many examples in showing that local min is a global min. Okay. All right. One last thing before we stop today. We'll talk about an interpretation of Lagrange multipliers, and this is called sensitivity analysis. And sensitivity analysis turns out to have applications of its own when you're applying constraint optimization in applications. For example, in in power systems, to actually, those of you who are in the power area, you might be solving a bunch of equations under constraints to set the various parameters of your power system, and you want to know what happens if the constraints change by a little bit. Okay, you want to know by how much will the optimum value change, right? That's called sensitivity. Okay, so let's talk about how that change is related to Lagrange multipliers for equality constraint problems. Okay, so here's the idea. So let's say we have x star, which is regular, and lambda. They are the local minimum and Lagrange multiplier, satisfying the second order sufficient conditions for the problem, the optimization problem. Okay. Now, suppose we perturb the constraint from 0 to u. So what happens then to the optimization problem is that we are minimizing f of x such that hx equal to u other than 0. Now we could show, and this is very technical, so I'm not going to do this here, but you can read the book if you're interested. There's a proposition 4.2.2 that shows that if I if for small perturbations, in other words, if U belongs to some small enough open sphere around 0, then there is an X star of U that's a solution to this problem and corresponding lambda of U, okay, for the perturb problem. So they exist. So you basically there exist Lagrange multipliers for the perturb problem, okay. And the important thing is that this X star and lambda are continuously differentiable functions of U. Okay, so this technical lemma is proved in your textbook, and I'm not going to go over that. And you could kind of believe it, right? So if you move by a little bit, then you still have Lagrange multipliers for the new problem, and that those things are going to remain continuously differentiable functions of U. Okay, so what we're going to show is by how much does the function, the optimum value, change. So it turns out, okay, so this is the claim. Claim is that if I now look at the new value, X star of U, this is the optimum solution, I look at the function at that X star of U and try and relate it to what the old value was, F at X star, before the perturbation, then they're related through the Lagrange multiplier this way, at least up to first order. So that perturbation is actually linear in U, and the linear coefficients are the Lagrange multiplier. Okay, up to first order. Okay. So for small perturbations, this is what it would be to a good approximation. Okay, so we're going to prove this. Again, to prove this, we are going to assume that X star of U and lambda of U are continuously differentiable functions, which is established in the book. Okay, I'm not going to go over that technically. Okay, to show this, let's define a function P. P is F at X star. So it's a function at the optimum value, X star of U. So P0, which is X star of 0, but X star of 0 is there's no perturbation. That's the same as X star. Okay. So what we really need to show is that the left-hand side, which is P of U as a function of U, is P of 0, which is F of X star, minus lambda transpose U. Are you guys still there with me?
Yes.
Yeah, okay, good. I have to keep checking. I don't know what happened to the internet. Okay. So, but basically what we want to show is that the gradient of this function P, which I said is continuously differentiable, we need to establish that the gradient of P at 0, sorry, not for this equation to hold, the gradient of P at 0 should equal lambda. Oh, sorry, minus lambda. No. Okay, so then P of U will be P of 0 plus gradient of P at 0 transpose U plus little o or norm of U. Okay, so we really need to show that the gradient of P at 0, gradient of this function at 0, should be minus lambda. Okay. So this is another interpretation of the Lagrange multiplier. That it's the rate of change of the optimum value as you perturb, as you move away from, as you perturb the constraint. Okay. All right. So how do we show that? Actually, it turns out to be just a very simple proof that's based on the chain rule. Okay, so I have P of u is f of x star of u. Sorry. So P of u is f of x star of u. And so I can take the derivative with respect to the x's first, and then take the derivative of the x's with respect to uj. So I'm computing each component of the gradient of p. So I'm taking the partial of p with respect to uj. So to get that, I'll write this as the summation, because I'm doing with respect to each component of x. Okay, first. So f is a function of x. So I'll take the partial of f star with respect to the kth component, and then multiply it by the partial of the kth component with respect to u. Okay. Now, so that's just the chain rule, right? So now the first order necessary condition says that I get this is for the perturb problem. So I know the perturb problem has a local min, which is x star of u, and corresponding unique Lagrange multiplier lambda I of u. So that times gradient of hi x star of u is equal to 0. That's the first order necessary condition of the perturb problem. From this, if I look at each component, I get the term I want. I get this, right? So the gradient of f for the kth component of the gradient will be exactly what I want here. So that kth component can be obtained as minus summation I equal to 1 to m lambda I of u times the partial of hi with respect to the kth component evaluated x star of u. Okay. Okay. So now, if I look at go back and try and plug that in here into this equation. So I've got this as a summation. So I'll make this into a double summation now. Okay. So minus summation k equal to 1 to n, summation I equal to 1 to m, lambda I, partial of hi, xk x star of u times the partial of xk of, x star, not x of u star, but xk star of u with respect to u. But then I can combine these two by using the chain rule. So this term and this term can be combined to just get the partial of hi with respect to u. So I can write that as minus summation I equal to 1 to m. So if I take let's see, I have to take this summation inside essentially, and then this summation of these terms is going to essentially look like this. Look like what I had here. This was expanded out into this. Now instead, I'll have the hi here, and that will be expanded in the same form. That'll give me this summation here. So it'll give me lambda I times the partial of hi with respect to uj. X star. Okay. Okay, so now I'm ready to compute this. What's the partial of hi of x star with respect to uj? What is hi of x star of u? What is this equal to? It's the perturbed constraint, right? So
0.
It's perturbed. So remember, we are perturbing so that
U.
so that's u. So if I look at the ith component, it'll be ui. Now, if you take the partial of ui with respect to uj, well,
identity.
It'll be identity. Well, it'll be not identity, but it's something close to that. So it's going to be 1 if I is equal to j, and it's going to be 0 otherwise. Right? So it's a delta function essentially. Okay, this can also be written as a delta function I minus j. Delta on integers. Yeah. So so if I look at now, plug that in. So if I look at the jth term here, so if you look at the summation, only the jth term in this summation will be non-zero. All the others will be 0. So if I look at the partial with respect to uj, on the right-hand side, what am I going to get?
Negative lambda sub j.
Negative lambda sub j. Very good. Okay. But that could be, that's a function of u, right? Oh, I didn't write down the function there. I should have kept the still a function of u all along. We're going to set u equal to 0 in just a minute, but okay. So the gradient has all these components. So the gradient is just the lambda vector at u. And so the gradient of p at 0 is minus lambda of 0, which is the unperturbed solution, which is minus lambda. Which is what we wanted to show. Okay, so let's go back and see what we proved. What we proved is that if we perturb the constraint by u, then the value of the function at the new optimum, okay, or the rate at which the value of the function at the optimum changes is given by a negative lambda. Right? Now this fact will actually turn out to be useful also in understanding optimization problems with inequality constraints, which is what we're going to consider after your midterm. Okay, so the plan for next week is to do more examples with equality constraints, and then on Thursday we're going to have a review session for the exam. So I'll go over all the material and take any questions that you might have. So we'll go all the lecture material, and I'll give you some flavor of what the exam is going to be like. Okay, and then you'll have your exam on Monday, and then after the exam, we'll start talking about inequality constraints. All right. Any questions? So no other questions, then let's stop, and I'll see you guys next week.
See you next week.